So the pendulum motion is due to a conservative force or a restoring force as well, which is the gravitational force. If we do a free body diagram of the pendulum, we will deal with forces. For instance, we have the tension of this string, and we have mass times gravity. In this case, the acceleration goes towards this direction, so it is convenient to state my y-axis in the direction of the tension, my x-axis in the direction of the acceleration, and so this will do an angle theta with the vertical. If I do my sum of forces, my sum of forces in the x direction, so this is going to be mass times gravity times sine of the angle is going to be equal, now in that side, mass times acceleration. Now, if we state the sum of forces in y, it will lead me to what? Perfect. Tension minus mass gravity equals 0. Okay, now the acceleration is going to be equal to the second derivative of the arc due to time. This is describing an arc, for instance, this arc. This is the arc. And we can actually express it as well in terms of the angle theta as length times the second derivative of the angle theta due to time, such that we can express the sum of forces in x as, well, mass can cancel, in this case, mass with mass, and we can actually have the length second derivative of theta due to time minus gravity sine of theta is equal to 0. Or we can rearrange this term as the second derivative of the angle minus gravity over length sine of theta equals. Very simple. We can actually state that the sine of the angle tends to the angle for small values of that angle, such that we can actually state a differential equation, which is the second derivative due to time g over L theta equals 0. This will lead, of course, to the expression that theta is going to be equal to the maximum theta, or the amplitude, cosine of omega 0 t plus the phase phi, and so omega 0 for the pendulum is going to be equal to the square root of g over L. So if we have a physical pendulum, not a simple pendulum, the forces that we're dealing with are exactly the same. For instance, we have the tension here, and we have another force, which is the weight, which is located on the center of mass. So mass times gravity. This as well has an acceleration of the center of gravity towards this direction, and we can actually state it makes an angle here of theta. We're going to deal with the sum of torques. So the sum of torques in this situation, the only one who generates torque, the weight, which means that in this situation we have the force, which is mg, times the lever arm. In this case is going to be v, the distance from the center of mass towards the axis of rotation, times the sine of the angle theta is equal moment of inertia times the angular acceleration. We can actually rewrite once again this equation as I times the second derivative of angle due to time minus mass gravity d sine of theta, or we can equal 0. Now, if angles are small, then we can do the same situation, that sine of the angle tends to the angle, such that we can have once again the differential equation minus mgd over I theta equals 0, where of course we can actually obtain that omega 0 is going to be equal to the square root, right, of mgd over I, or we can actually state is going to be equal to the sum of torques over the moment of inertia.